Hello everyone, my name is Alex Dahl. I'm a mineral grinding and comminution expert. And in this video, I want to talk about the 5 types of Bond Work Index numbers. So Fred Bond introduced the work index to the world in the early 1950s, and it has now become one of the most commonly used measurements of ore grindability in industry. It's so common, in fact, that you'll often hear people talk about the work index. So I've got a couple of examples here of publications where people say the bond work index. But there's actually no such thing as the work index. There's actually multiple work indices that describe an ore. So this video will describe each of the 5 bond work indices, quick description of what they are, a description of which one you should use for a particular calculation. Now, all of these work indices are valid for use in the bond third theory equation. Any one of these 5 can appear in an equation of this form in this position, depending on what you're doing and what data you have available to you. So some housekeeping. For the purposes of this video, I'm going to say that only specific energy consumption has units of kilowatt hours per ton. So that's the E value in the Bond third theory equation. I'm going to describe work index as having units that are metric, or this much more complicated expression you see here that I'll explain a little later on in the video. So the 5 work indices are the work indexes for ball milling, for rod milling, for crushing. These are all laboratory tests. And then there's an operating work index, which is kind of generic and can be applied to anything. We'll talk more about that. And then the 5th one is more of a concept work index, which is related to something called the Hooke conjecture, which we'll get into. So starting off with the Bond ball mill work index, the WIBM value is determined using an expression that Fred Bond generated based on some empirical analysis, using an apparatus which is a tumbling mill of a particular size, particular speed, that has a particular liner arrangement. All of these have been standardized. And there's a revolution counter that the operator uses to specify the number of revolutions for each cycle of the test. Something to know about this test is it is only valid if you have a proper feed size that has been stage crushed in a way that corresponds to the bond procedures. If you, for whatever reason, you don't have a standard feed size, you need to apply a correction. So it's not valid to just take a laboratory HPGR, pull a product out of that, and just stuff that into a Bond ball mill and say, oh, look, the ball mill work index has changed. Actually, it might not have. All you've done is you fed it with an invalid feed. The work index for ball milling changes as a function of the product size, and this is baked right into the Bond procedure. You must choose a closing screen that approximates what will give you a P80 of what you would see in the plant. So here's an example of a paper published by Josephine and myself, where multiple work index numbers have been computed in the ball mill apparatus at different closing sizes, and you can see that the work index changes. And the method of Josephine and Dahl can be used to adjust the P80 for a test if you want to do modeling at a P80 different to what you ran the test at. So when you're using the ball mill work index in the third theory context, it's going to be valid basically from its feed size down to its product size. And if you deviate too much from that size range, you're going to need to apply adjustments in order to use it in the third theory context. So let's just start up a leaderboard here of where the ball mill work index fits in the bigger picture. You're looking at feed sizes of 1 to 2 millimeters down to product sizes, 100, 200 micron, very common. Occasionally you'll go coarser to 400 microns, but weird things start happening when you go much coarser than 250 to 300 microns. The next work index we'll talk about is the Bond rod mill work index, which is determined using the Bond rod mill grindability test. So the apparatus is a mill with a wave liner that gets rocked as the test is operated. The machine runs at 46 RPM as a revolution counter. There's multiple cycles of the test. The apparatus must be rocked every 10 revolutions as the test is progressing in order to avoid building up material on the ends of the mill where the rods can't reach. So rocking the mill brings the charge back inside the rod charge, and that's necessary to get a reliable number. Beware that there are non-standard apparatus out there, particularly in Australia. I'm aware that the JK lab has a proper rod mill, and several of the other labs have non-standard smooth liner machines which may not be rocked. Those non-standard machines will give you a rod mill work index, but it will not give you a Bond rod mill work index. There are models specifically calibrated to that smooth liner, but they're not the ones that consultants like me use. So on the leaderboard, the rod mill is going to work with a much coarser feed size, 8 to 9 millimeters, 10 millimeters. And the product size it takes you down to is on the order of a millimeter. So you can see that there's some crossover between the product size of the rod mill and the feed size of the ball mill. The next test we'll talk about is the Bond Low Energy Crushing Impact Test, which determines the crushing work index, the WIC. You'll also see this referred to as the LEIT, L-E-I-T for Low Energy Impact Test, or CWI for crushing work index. In the literature of Bond and the Alice Chalmers people of the 30s, 40s, 50s, when these apparatus were being proven out, you'll see two different apparatus used in the literature, one of which is commonly called the bicycle wheel. You see an example of that on the left. And then there's another one is based on the pendulums, which you see an example of on the right. In theory, both of these are valid apparatus for determining the low energy crushing work index. The test is done with very coarse specimens. So you basically go out and you take a bucket full of rocks, where those rocks are 50 to 75 millimeters nominal dimension, so 2 to 3 inches. You're going to run multiple specimens through the machine. So you put a specimen in the machine, you whack it with the pendulums until the machine manages to break the rock. Then you put the next specimen in, whack it with the machine until the rock breaks. Do that 20 times, and then you average the joules per millimeter of rock dimension that was needed to break each of the specimen. And then that gets plugged into an empirical equation to work out the WIC value. Some issues with this test is that it has poor reproducibility. The two types of apparatus should be equally valid because they were both described in the literature when Bond was doing his calibrations. My experience and the experience of others is that these two do in fact give different results, and it can be kind of difficult untangling what you're seeing. For my purposes, I treat both types of apparatus as being equal, and I just accept that there's going to be variation depending which lab you do the test at. The WIC result in a geologically young rock, so places like the Andes, the Canadian Western Cordillera, the Ring of Fire around the Pacific, for example, it's going to be dominated by fractures in the rock, and it's quite common for this work index to be substantially less than the ball mill and the rod mill work index numbers. Now, I mentioned that the test has poor reproducibility. Because of the coarse nature of the test, the equipment sizing is generally not sensitive to this value. 1 over the square root of a great big number, like a coarse F80, of course P80, means the overall fraction is very small. So that's typically what we would see running a WIC value through the third theory equation. It has a low impact on the overall specific energy consumption of a circuit. This is going to be the last of the laboratory work indexes that we're going to look at in the video. And up on the leaderboard, you can see that this is going to be the coarsest of the laboratory tests. Product size isn't actually measured in the test, but you're going to get fragments of multiple millimeters in nominal dimension. The only thing that's really specified in the test is the feed size should be in that 50 to 75 millimeter size range. The next work index we will talk about is the operating work index. And it's measured for any continuous size reduction equipment that have power draw, and this will be the mechanical power at the shell of the device, the shell of the mill, pinion power, that sort of thing. You'll have the throughput in terms of metric tons per hour on a dry feed basis. So again, you have to account for the moisture that's in your ore and take that out before you plug it into an operating work index computation. You need a feed size and you need a product size measured as the 80% passing in the feed to product. Operating work index is not restricted to classical grinding equipment. You can measure it for ball mills, you can measure it for sag mills, you can measure it for an HPGR, you can even measure an operating work index for a flotation cell, right? You have power draw, you have throughput, you'll have a change in size between the feed and the concentrate of a float cell. You can measure this. What you do with that, that's up to you. So the way you compute an operating work index is you just run the third theory equation backwards and you solve for the work index since you know the specific energy consumption and the feed and the product size. So, the equations on the screen basically show you how you do that. The specific energy consumption is always measured using the mechanical power, not the electrical power. If you have a measurement that is looking at the electrical power going into a motor, you need to apply the motor efficiency to turn that electrical power into mechanical power, and possibly gear reduction allowances if there's something like a gearbox. The tons per hour should be dry tons per hour. It should not be wet. And you might need to validate the particle size distributions just in case there's some noise in your particle size distributions and an erroneous point might give you a wrong 80% passing size. So here's a particle size distribution for a secondary crusher product. And you can see it's a pretty noisy looking data set. So a reasonable question to ask is how reliable is this point, which is what really drives the 80% passing size? We can look at some models that describe particle size distributions and fit them using the granulometric software. And we can compare how robust this point is to some of the typical regression equations we can use to describe particle size distributions. So in this case, the Rosen-Ramler distribution gives us a fitted 80% passing size of 126 millimeter, which is almost exactly the same as the 128 millimeter you get just by looking at these two nearest neighbors. So that suggests it's a reasonably robust number. Some of these other models, like the Godin-Schumann model, predict that the 80% passing size for the crusher is actually a little bit less. So if that regression model doesn't really like this data point and thinks it should be a little bit further to the left. So with all of these different models, you can kind of judge for yourself which one of them do you think best describes the particle size distribution. So in this case, I think the Rosen-Ramler is not a bad choice. It works well below the 80% size down to the range of 10 to 20% passing. Most of these models don't work really well with the one or two most coarse particle sizes. So this, looking at the Rosen-Ramler distribution, tells me that we can rely on the nearest neighbors method, that this is a robust number that we can use when we're doing our work index calculations. So what is the operating work index generally used for? Commonly it's used to compare the efficiency of a circuit when you see things like the power draw changing and particle sizes changing simultaneously. You can't really use specific energy consumption to measure grinding efficiency if the feed size is changing or if the product size is changing. Operating work index can be used to make small adjustments to things like the specific energy consumption for a small change in P80, for example, if you wanted to know how much power do you need to grind a little bit finer. You can compute the operating work index for individual pieces of equipment, but you can also do it for the entire circuit. You can sum the power of all of the equipment, and then the result is the operating work index for that whole circuit. So let's look at an example of how we can use operating work index to measure the efficiency of a grinding circuit. So I've got here a sagmilling.com simulation of the Fort Knox mine in Alaska. There's some published data out there with their mill sizes and so on. We have the feed size into the circuit. We have the product size coming out of the circuit. We've got 3 work index numbers, one for crushing, one for rod milling, one for ball milling. And I'm using Barrett's equations to predict the total circuit specific energy consumption. So that's basically the specific energy consumption from the sag feed to the cyclone overflow. And then we also can generate the specific energy consumption for the sag mill, for the ball mill, and a little bit for the pebble crusher, as well as the circuit throughput. So the overall operating work index for the circuit is actually a little bit higher than what we see in the laboratory tests by 20 to 25%. And that's normal. This is why we say that sag mills are a little bit less efficient than classical equipment like rod mills and cone crushers. And the typical numbers you see thrown around are, 10%, 20%, 25%. We're right in that range here with a 27% increase in work index for the operating work index versus the ball mill work index. Assuming that the ball mill work index is a typical work index describing this ore. You can also work out the operating work index for an individual stage in the circuit. So if we look at just the ball mill stage, you've got the feed is going to be this transfer size. The product is going to be this P80 size. We've got the power in the ball mill circuit and the throughput. With that, we can compute the specific energy consumption of the ball mill stage, and the operating work index turns out to be less than the laboratory ball mill work index. This is relatively normal, and this is what we call the phantom cyclone effect, where a sag mill often makes more fines than what you would see in a classical circuit, especially with rod mills. And those extra fines pass into the ball mill cyclone and then get classified immediately out into the product. So those fines never actually make a trip through the ball mill, which reduces the amount of work that the ball mill has to do. And that manifests as an operating work index of the ball mill that is less than the laboratory measured work index. So the ball mill looks more efficient than what the laboratory says, but the overall circuit is slightly less efficient than what you would expect if you look at things like the Bond standard way of measuring circuit efficiencies. If you compare the operating work index to the laboratory work indexes and so on. So here's the operating work index up on the leaderboard. It applies almost always to plant equipment. And it can have basically any feed size, because you could actually work out the operating work index of blasting, going from ridiculously coarse sizes And you can work out an operating work index for fine grinding mills like ISA mills and Verdi mills. It's not a great way to measure the efficiency of those fine grinding mills, but you can run the math and get a number. The final type of work index is going to be a bit more of academic interest. It's work index in the Hucke conjecture context. So, Professor Hucke from Finland in 1962 observed that ore breakage models don't always fit um, across a wide size range. And he said for a hypothetical ore, you're going to need to use different models in different size ranges. And what he basically proposed is that the rate of change of the consumption of specific energy, the dE, for changes in size, the dx, should be some differential equation with a constant coefficient and an exponent on the size term, which is going to be variable over wide ranges of sizes, but it's going to be approximately constant over short ranges of sizes. So one way that you can unravel the differential equation is you get one solution that looks like this, where the specific energy consumption equals some other constant K with the feed and the product sizes to some exponent, where in this example, we're saying that the exponents are constant. So over a short size range, that's a reasonable approximation. Now this looks a lot like the Bond equation. So in this example, in this framework, the work index is 1/10 of the value of K in the Hucke conjecture solution for the special case where the exponent on the size term is -1/2. So 1 over the square root of a number is the same as that number to the power of -1/2. So this, I would argue, is the work index. It's the most generalized form. It's just 1/10 of this coefficient in this Hucke conjecture context. So if I want to put this up on the leaderboard, it doesn't have an apparatus. It actually comes out of the theoretical framework. And what where it fits into Hucke's conjecture, it fits into a much larger universe of different models. So the signature plots that you get for fine grinding are part of the Hucke conjecture universe. Coarser blasting models, for example, can fit into the Hucke conjecture universe. The Bond model just kind of fits in that rod milling, ball milling size range. But in this conjecture, it could be any size range. So I talked a bit at the beginning of the video about the units of work index. If we say that the actual definition of work index comes from this universe of models in Hucke's conjecture, the way that Bond developed his model using ratios isn't really relevant anymore. We can say that the value of 10 in the work index equation is just a meaningless scaling factor. When Bond developed it, he was working with ratios, and a ratio to a size of 100 microns was convenient to use. It was easy to calculate. That's why the 10 is there. That to me is an antiquated way of describing a work index. This more modern version doesn't use ratios, and we can set the 10 to be unitless. It's just a meaningless scaling factor. So if you look at the units in the third theory equation and just crank them through, you end up with a new set of units for the work index that are distinct from specific energy consumption. And that's important because I see numerous examples of people trying to do mathematics with work indexes and add them or subtract them from specific energy consumptions. in the erroneous belief that the two quantities with the same units are somehow additive. If we give people work index in a form that it is not obviously the same as specific energy consumption, that mistake goes away. So another way that we can describe the units of work index is an example on the right. If you find that more convenient, you can use that. They're equally valid as long as people understand work index does not have units equal to specific energy consumption. These two are different quantities. They are not the same thing. So in review, we have a Bond ball mill work index, which obviously works for ball milling size ranges. We have a Bond rod mill work index, which is often used in Barrett's equations to describe a large part of what a sag mill does. We have a Bond crushing work index, which obviously is used for checking the motor sizes on crushers. And it's also used in Barrett's equations to describe the very coarse part of what happens in a sag mill. There's an operating work index which you can measure in your operating plant, and you can compare that to the laboratory work indexes to try and get a sense of the efficiency of your plant. And then finally, we've got the more generic work index as part of the Hucke conjecture universe of grinding models. And that fifth one, the least useful one, is actually what the work index is. It's the most generalized of all of these work indexes. So with that, I'll say thank you for watching the video, and we will see you in the next one.